And here you thought that metals were just these innocent atoms on the periodic table that are useful for our everyday life. Little did you know that metals are actually scheming communists. Today we're going to be talking about metallic bonding and why metals are communists. By the end of this video, you should be able to distinguish the difference between ionic, covalent, and metallic bonds and describe their differences after you learn what a metallic bond is now, our final chemistry bond. Metals are in fact useful everyday items, so I would like you to think of at least 3 items made out of metal that you see or use on an everyday, day-to-day basis. I have included a few pictures to get your mind going of things that I see or use every day. I do use my car, and street lights are very useful, made out of metal, and the cooking pot, definitely use that every day, also made out of metal. What are 3 things that you use or see every day that are made out of metal? I'm going to assume that you at least thought of 3 metal items, and that is what we're talking about today, is our last bonding type in chemistry, which is metallic bonds. And what makes them so different and unique from the other 2 types of bonding that we've already talked about. As a refresher here, ionic bonds are between a metal and a nonmetal. You have a charge attraction between 2 atoms, a cation and an anion. Covalent bonds are between 2 nonmetal atoms where they're sharing electrons either equally or unequally. And now moving on to this metallic bond. We have metal atoms that are literally surrounded by a sea of electrons. This is really a huge difference from the ionic and covalent bonding. We're not sharing electrons equally between 2 atoms. We're not stealing or gaining electrons. Literally, all of the positively charged nuclei of the metal atoms are hanging out together, and all of their valence shell electrons are buzzing around all of them. So none of them own their own valence shell electrons because it's owned by the community of positively charged metal atom nuclei. So literally, a metallic bond is the attraction of the positive metal atom, the nucleus, the protons, to a sea of surrounding electrons that are shared in a whole community of these metal atoms. So literally think about not a single atom owning its own valence shell electron. There's literally not an electron that's specifically bonded to a particular metal atom. It's all about and everywhere. It's free to move wherever it so chooses. So from the electron's perspective, this is great. It can kind of bop around and see all the different kinds of parties going on with the different metal nuclei. For the metals themselves, they're just hoping an electron comes by at some point in their sea of electron sharingness. So as you can see in this picture here, literally those little E's with the minus, that's the electron buzzing about all the different positive nuclei for the metal atoms present. Those electrons are not staying put, they are in motion and they're buzzing around all of the metal atoms. But how on earth is this happening? How can there just be electrons flying freely all willy-nilly and not connected to a single particular positively charged metal atom nucleus? This is because there's lots of overlapping orbitals. This allows the electrons to move freely throughout the entire metal substance. So what we say then is that the electrons can act delocalized. They don't have a location that's specifically meant for them. Kind of sad if you think about it. They don't have a home they can just go to that's their home forever. They have like a million homes that they belong to. But in a positive note, they can explore the world because they don't have to stay in their own nucleus. They're shared in the sea of electrons and they're free to roam. Roam if you want to, all around the metal atoms. So let me show you what this would look like in terms of a shell model depiction for sodium. Sodium's electron configuration I've written up here so you can kind of see the valence shell that we'll be talking about is the 3s1. But let's draw a community of sodium atoms together so you can see how their valence shell electrons would interact with one another. Okay, now that we have our shell models all drawn so you can kind of see how they're going to interact with each other, I'd like you to take note that these are the valence shell electrons that are interacting for a metallic bond. So we're not talking about all of these electrons here. We are talking about the 3s1. We are talking about the third level orbitals overlapping, and that's where the electrons are being shared between these positively charged metal atoms. So specifically, we're looking at this outer ring for each one of these sodium atoms, sharing their one electron amongst the entire community. Now, of course, in a real metal, this is just a very small depiction of what's going on. There would be enough metal atoms present so that each metal atom itself would have that full outer shell. Again, metals want to be like the noble gases too. They also want to have a full outer shell, a full valence shell. They're just going about it a different way by filling up their outer shell by sharing it constantly with all of its neighbors nearby. So then what's happening here? Let's depict all of this here by a single orange circle. Now it's a lot easier to see how the valence electrons are going to be interacting with each other in the empty overlapping orbitals in the valence shells. Coincidentally, my picture kind of looks like green eggs at the moment, and I feel inclined to also include ham here. Green eggs and ham. All right, we have green eggs and bacon now. Anyways, so what we can see now is that, say, this electron here is going to be buzzing around all these other different valence shells, all these overlapping orbitals, and passing all the way back and forth continuously. It doesn't stay localized around any single one atom. It can go wherever it pleases at any given moment. And check it out. This way, the whole system of metal atoms end up having enough valence electrons in their empty orbitals, their overlapping orbitals, to make all of the metal atoms present feel like they're a noble gas. So they have a completely different method of attaining noble gashood than the other ionic and covalent bonds did. In other words, this is why I kind of feel like metals are like a community or communism. Because there's no single ownership of electrons anywhere. They all own the electrons equally. So this freedom to move about electrons gives metal some very special properties that we as humans have utilized to our benefit over many, many years. So a few of these properties that you should be familiar with are as follows. First, electrical conductivity. So electrons are flowing through the metal. In other words, they're not attached to a singular atom, which is why they can flow and cause electricity. So these electrons can basically carry their charge through the metal and zap you if you touch it. There's also thermal conductivity. This is the reason why when you touch the pot handle on the stove after it's been sitting there for a while, your pot made out of metal, that it will burn your hand essentially, which I learned the hard way because now I have a gas stove and apparently you can't touch even the handle on the top of the lid of a pot without scalding your hand. Thanks to the fact that metals have these free moving electrons also means that they can move that heat really well. There's also malleability, so the ability to form metal into thin sheets. So we can gold plate things with thin sheets. We can turn metal into coins for currency. That property is called malleability. And also ductility. This is the ability for metals to be formed into wires. And we use those wires for computers, for internet, for like everything that we use nowadays. So what we see then is thanks to this communistic outlook of metals on life, we end up getting a lot of really beneficial properties about metals that we can utilize. And some properties that are also quite dangerous. Now, this is the same reason why I put outlet covers in all of my outlets throughout the house so that my daughter doesn't take a fork and shove it into the outlet. Funny side note story here, my mom actually did that when she was little, and she actually comes from Europe. And their electrical outlets are actually even higher in conductivity, so they have more current passing through them. And so she was that kid that stuck the fork in the outlet, and she got fried, man. Like her heart was palpitating for a while. And yeah. Another fun side note here about electrical conductivity is that you never want to be the one that completes the circuit. I did that once on accident. I was taking out a microwave. I was taking out one of those fume hood things that go over a stovetop to install a microwave. and well, I'm not an electrician, so I forgot to turn the electrical panel off in my house before I did that. And I was holding one end of the wire, and then I reached over to grab the other wire, and let's just say I did like one of these numbers for a minute. And yeah, that ended up like seriously electrocuting me, and it was hard to even let go of the wires. Yeah, not a fun time. Not fun to feel like you're literally going to have a heart attack and die because all of the electrical current is passing through your body. And you've now become essentially a wire for the electrons to pass through and electrocute you. If you have any funny electrical conductivity stories to tell, please tell me in the comments below. I'm sure they're hilarious. And also, malleability, in addition to making thin sheets for coins and for gold plating and for jewelry and for all these other things, is the whole reason why swordsmithing was possible. And the ability to make like shields for war and battle and all that jazz, you know, like kind of the whole thing that, so kind of really important in history, the fact that we actually had weapons to use, and all of that was due to metallic's property of having a sea of electrons. So let's delve a little bit farther into this orbital overlap thing for metallic bonding. So the valence number for most atoms is a really small number. So typically, if you look at the metals, they usually have like a 1 or a 2 or a 3. They don't really have a lot of electrons in their outermost valence shell. It's a small number, typically. So therefore, what we can say is that there's a lot of empty orbitals, just empty space in the highest energy level. And because there are all these empty orbitals, that conveniently gives the electrons a place to bop around to. If you remember from the electron configuration and orbital diagrams lesson way back when, the d orbitals are just below the highest orbital level you can get to, and those d's are all in the transition metal range. And they may have a lot of vacancies. So you can think of it literally as giant hotel buildings or giant apartment complexes with nobody there, like Ghost Town, all furnished, all ready to go, but nobody there. So these outer high energy orbitals overlap with one another, and this allows the electrons to flow freely between the different metal atoms with their overlapping high energy orbitals. I know you've got to be thinking to yourself, well, how do we name these bonds, Mrs. Duck? Because covalence and the ionic bonding had a lot of complicated naming schemes just to figure out how to name them. Well, you're in luck. The metallic bonds are the easiest to name of all. You just simply give them the name that's on the periodic table and done. So for example, K is potassium. It's not potassiumide. It's not sodiumide for Na. It's just sodium. It's just calcium, just magnesium, just aluminum, just zinc, just iron, and you're done. So there's no special naming scheme or rules here. Just look at your periodic table and that's its name. So now let's compare our different bonding types all together. The MACROscale properties, so this is stuff you can see with your eyes or things you can test. MACROscale, not micro, so we're not talking about like atomic level here. Just what are the differences between these three different types of bonds, typically overall? For ionic bonds, we see that those are typically brittle and or hard substances. They often dissolve in water, and they conduct electricity when dissolved in water. So ionics are typically salts, literally like table salt or any other kind of crystalline structure, like a crystal lattice, if you remember from a past lesson. And when you take those, you can put them in water, they're soluble in water, and then once they dissolve in water, they conduct electricity. Covalent bonds tend to be soft and or hard, so you can have one or the other. Those covalents don't necessarily have a specific type of feel to them all the time. Unlike ionic bonds, where they often all dissolve in water, the covalent bonds have a stipulation on when they dissolve in water. It has to be a polar covalent molecule in order for it to dissolve. If it's a non-polar molecule like oil, oil would not dissolve in water. So you have to have something that's polar, like sugar, covalently bonded, that will dissolve in water. Now the difference here though is that if a covalent bond like sugar were to dissolve in water, it doesn't conduct electricity. And of course what we talked about today are metallics. Metallic bonds are usually hard, but sometimes they're soft. Sodium metal can actually be cut with a butter knife. It just slices right off like a stick of butter. However, I wouldn't recommend trying to do that with, say, silver. You might not get far. And obviously, waters don't just spontaneously dissolve in water. You couldn't just stick, like, I don't know, this pair of scissors in a cup of water and expect this metal to dissolve. It might rust over time, but it's not going to dissolve. And metals are also malleable and conductive, so they do pass electricity through them, and you can bend them in such a way or create them into flat sheets by smashing out the atoms into thinner and thinner sheets with a hammer. So then let's delve into the atoms itself and talk about the microscale properties of these bonding types. For ionic bonds, it's always going to be a metal and a nonmetal, and we're talking about the theft of valence electrons, so the full taking of valence electrons or giving, and that creates that cation or anion property. A loss or gain of electrons creates a positive or negative charge on the atom. Then we also see that those charges are going to attract to each other to balance out to zero, to be neutral, and they form lattices. So there's lots of structures together. It's not necessarily just one molecule. There's typically a whole structure and network of molecules working together to create these little ionic lattices. Now we have covalents, and covalents are always composed of nonmetals and nonmetals together. They're sharing those valence electrons, again, via orbital overlap, the same kind of share that we have for metallics, but there's an equal or unequal sharing that's either polar or nonpolar. And we can represent these covalent bonds by Lewis dot diagrams and show that they are double, single, or triple bonded between each atom type. Last, we have metallic bonds, and that's all the metal atoms. All the metal atoms participate in metallic bonding, and only metal atoms. And metals with metals is the only kind of bond that would be metallic. They do this by having a C of the highest energy electrons, the valence electrons in specific, sharing them all amongst the nuclei of positively charged metal atoms via orbital overlap. So to summarize all of our bond types, metallics, C of electron, held together by a C. So the key takeaway here is to think about what the electrons are doing. As with anything in chemistry, electrons are key. In metallic bonds, the electrons are what holds together metal atoms via a sea of electrons, a community, communism sharing of electrons. In nonpolar covalent bonds, we're being held together by the sharing of electrons equally. In polar covalent bonds, we're being held together by the unequal sharing of electrons in orbital overlap. And in ionic bonds, we're literally held together by a full positive or a full negative charge on an atom, causing those two atoms to come together and be neutral. Before you move on with any further lessons, you should check yourself before you wreck yourself and make sure that you can answer all of these questions. Go ahead and pause the video here and make sure that you understand the answers to the following 7 questions. How do the electrons behave in ionic, covalent, or metallic bonds? What are the different bond types composed? What type of atoms make up the different bond types, ionic, covalent, and metallic? And what are the physical properties that you could test for? Say you had some unknown chemical and you wanted to know if it was covalently bonded, ionically bonded, or metallically bonded. How could you test that chemical to determine what its bond type would be? Once you feel confident that you could answer all of these questions without batting an eye, we'll take it to the next level in our next video about types of chemical reactions. That's all, ducklings. Give me a quacks up and please subscribe to my channel for more educational content. Have a ducky day.
No ducks, no glory.